Hello student, this is Vijay Ushir. In the last lecture, we have started the first chapter, that is thermodynamics. So in that we have studied the different basic concepts also, and also the concept of heat capacity. So in this lecture, we will study the reversible, irreversible and adiabatic work of expansion. So first we will study the reversible work of expansion. So what is the reversible work of expansion? So consider a gas enclosed in a cylinder with weightless and frictionless piston. Means a gas is enclosed in a cylinder having a weightless and frictionless piston, and the pressure applied on the gas on the piston is due to infinitesimal amount, say as a dp. So small amount, that is a dp, is the pressure change, and therefore the small change in the volume, that is given by dv. So consider this gas is enclosed, this is a cylinder, gas is enclosed in this cylinder, this is the piston. So the pressure applied on the gas is the pa, and the pressure applied by the atmosphere, that is p. So and the small change in volume, that is here dl is written, or also it is called as a dv, small change in the volume. So this is a piston. So this is the diagram for the gas enclosed in a cylinder and having a less frictionless piston, and the pressure applied on the gas is dp, and it is reduced by the smaller amount called as a dp and small change in the volume called as a dv. Therefore, how we can write the reversible work done? dw reversible is equal to p minus dp into dv. But we know that dp is very small because it is an infinitesimal amount. Therefore, what we can write for p minus dp? So we know that for the work done formula is W is equal to minus P into dV. Therefore, for the reversible process, the change in pressure is dP. Therefore, we have written dW for the reversible is equal to P minus dP into dV. But dP is very small. Therefore, P minus dP becomes equal to P. Therefore, we can write dW reversible is equal to P into dV. And if the same gas is allowed to expand irreversibly, so this is expression for the reversible expansion. So this gas, if allowed to expand irreversibly, let's say in a vacuum against the constant external pressure of a 0. So what happens? The work done for the irreversible process dW irreversible is equal to P into dV. But what is the condition? Against the constant external pressure of a 0. So if the pressure is 0, what will be the work done? 0 into dV, that is a 0. Therefore, for the irreversible process, work done is 0, and for the reversible process, work done is P into dV. So, for the reversible process, to produce more work than the irreversible process, because we know that in the irreversible process, what work is obtained? It is a 0. Therefore, in the reversible process, the work done obtained is always maximum. So, the work magnitude in reversible process depends upon the magnitude of difference between the pressure applied on the piston. So, whatever amount of pressure is applied on the piston, that pressure is affecting on the work magnitude in the reversible process, and also the pressure of the gas, means the both the pressures are responsible for the work magnitude in the reversible process, that is the pressure applied on the piston and the pressure applied on the gas, and the work done will be maximum when the difference is small. So the difference between the pressure applied on the piston and the pressure of the gas, this difference, if it is small, therefore the work done will be maximum. Therefore, for dW maximum, we can write for the reversible process is equal to P into dV. Therefore, we can write for dW maximum is equal to dW reversible into PdV, and the total work done from V1 to V2, from volume V1 to V2 is obtained by integrating this equation. So if we integrate this equation, W max is equal to, so for maximum work done from volume changes from V1 to V2, because the process is a expansion. So V1 to V2 P into dV. This is called as equation 1. So For 1 mole of perfect gas, we know the equation, that is PV is equal to nRT. But for 1 mole, it is PV is equal to RT. Therefore, if we rearrange this, so P is equal to RT upon V. So if we put the value of this P, W max is equal to integral from V1 to V2 RT upon V into dV. Therefore, for W max, we got, so what is the integration of 1 upon V? Because R is a gas constant, which is a constant, T is a temperature, is also constant. Therefore, integration of 1 upon V into dV, it is a ln V. So ln of V, integration of 1 upon V is ln V, and by putting upper limits minus lower limit, we can write ln of V2 minus ln of V1. Therefore, we can write in the simpler form, W max is equal to RT ln V2 upon V1. This is called as equation 1. And also we can, how we rearrange this equation, W max is equal to minus RT ln V2 upon V1 is written as V1 upon V2 by taking minus sign common. But when R and T are constant, so we can write the equation PV is equal to RT, but R and T are constant. Therefore, we can write for the two conditions, that is initial and final conditions, that is P1 V1 is equal to P2 V2. Therefore, we can write P1 upon P2 is equal to V2 upon V1. Therefore, W max, for the W max, what we can write? W max is equal to RT ln P1 upon P2 from equation 1, because what is the value of P2 upon V1? V2 upon V1 is equal to P1 upon P2. Therefore, for the W max, we can write W max is equal to minus RT ln P2 upon P1, because the minus sign is taken common. Therefore, for P1 upon P2, we can write P2 upon P1. And if we convert this ln to the logarithm, so we multiply by the 2.303, and therefore by multiplying this equation by 2.303, we got W max is equal to 2.303 RT, ln get converted into logarithmic form, into bracket P1 log of P1 upon P2. So this is the expression for the maximum work done, that is obtained in the reversible process. That is W max is equal to 2.303 RT log of P1 upon P2 by changing the base from ln to logarithm. So what are the different conditions? So if the expansion is in the vacuum. So if we do the expansion in vacuum, so we know the equation for the maximum work done, that is W max is equal to 2.303 RT log of P1 upon P2. So in the vacuum means what is the condition? So against the zero external pressure. So in the vacuum, if the external pressure is 0, that is P is equal to 0. Therefore, what we can write? If P is equal to 0, therefore all becomes 0. That is maximum work done obtained in expansion in vacuum is 0. Therefore, W max is equal to 0. Next, if we do the expansion against the constant external pressure. So here we know that there is change in pressure from P1 to P2. So if we do the expansion against the constant external pressure, therefore what equation we got? W max is equal to P into bracket, because pressure is a constant, P into bracket V2 minus V1, and P is the external pressure. So W max, or maximum work done obtained by the external constant external pressure, is W max is equal to P external, that is external pressure of atmosphere, into V2 minus V1 can be written as delta V. So these are the two conditions for the work done for expansion in vacuum and expansion against the constant external pressure. Next is the irreversible work of expansion. So consider this. Gas is enclosed in a cylinder having the pressure P1, volume V1, and temperature is a constant. And the external pressure, that is P external, is equal to P2. This is the initial state. And final state, same gas is enclosed in a cylinder, the pressure changes to P2, volume changes to V2, and temperature remains the constant. And here the pressure becomes P2. But here the pressure is equal to P2. External pressure is equal to P2. This is a final state. So Suppose a gas is enclosed in a cylinder and external pressure is allowed to expand suddenly. This external pressure P external is allowed to expand suddenly from initial state to final state. So what happens? Pressure changes from P to P1 and P to P1, and also in the final state pressure changes from P to P2. So this is the initial state and this is the final state. So work done in the irreversible process, how we can write in the equation form. So W irreversible is equal to V1 to V2 P2 into dV, because the pressure is changed, because if we have to allow the gas expand irreversibly and suddenly. Therefore, V1 to V2 P2 into dV. Therefore, we can write P2 as a constant, P2 into bracket into integral of V1 to V2 into dV. Therefore, W work done for the irreversible process can be written as P2 into bracket. What is the integration of dV is V, and from by putting the upper limits minus lower limit, P2 into bracket V2 minus V1. But we know that P1 V1 is equal to nRT. There is a ideal gas equation. So these are the P1 V1, that is the initial condition. nRT, these are the all are the constant. Therefore, for the volume V1, how we can write? V1 is equal to nRT upon P1. For P2 V2 is equal to nRT, how we can write? V2 is equal to nRT upon P2. Therefore, for the irreversible process, P2 can be written as nRT upon P2 minus nRT upon P1 by putting the value of V2 and V1. And therefore, work done for the irreversible process can be written as this nRT is taken common outside and P2 is multiplied in the bracket. Therefore, P2 upon P2 gets 1. Therefore, 1 minus this P2 upon P1. Therefore, work done for the irreversible process, the expression for the work done for the irreversible process can be written as W irreversible is equal to nRT into bracket P1 minus P2 upon P1. So this is the expression for the irreversible work of expansion. So in the next lecture we will study the last, that is adiabatic work of expansion. So in this lecture we have studied the two work of expansion, that is a reversible work of expansion and irreversible work of expansion. And adiabatic expansion we will study in the next lecture. Thank you.